Hello, hello everyone. Today I will work on chapter 3 review for the first part. In my current class, I have to had cover up to 3.3 only. And so what I plan to do is I cover the material from this chapter review that went up to 3.5. But I will identify which one we already cover, again, assuming that I already covered up to 3.3. And for the ones coming from 3.4, I will identify that later on. Actually, let me just do it now. So the questions that comes from section 3.4 are this one here. That's section 3.4. Okay. And then after I'm done with number 16, I will interrupt that with question number 33 to 37 because those are from 3.2. Yeah, I think it's 3.2, 3.3. Okay. And then I go on to 17 to 28, which is from section 3.5. Okay. Oh yeah, it does say it here. Okay. Now the thing is, like, section 3.5, you will see later on actually encompasses some parts in chapter 2 and 3.1, 3.2, 3.3. Okay. So basically that summarizes the a lot of sections into this one section. Okay, let me start. Number one, let me do it here on the right hand side. Find the local and absolute extremes value. So local maximum, local minimum, local absolute maximum, absolute minimum in a closed interval. Okay, so let's do it. So fx equals to x cubed minus 9x squared plus 24x minus 2 in on in close interval 0 to 5. Okay, so f prime x is 3x squared minus 18x plus 24. I can factor the 3 out. And I get 3x minus 2x minus 4. So the critical numbers are x equals to 2, x equals to 4. Now notice that this is in a closed interval, right? So you can do second derivative tests on this polynomial to see if it is local max, local minimum. But because it's on in a closed interval, it's not necessary. We need to do is just find the value at f2, find the value at 4, and don't forget we need to also check at the endpoints. Okay. Since this is a polynomial, let me remind you that we can actually check the value of a function of a polynomial at a certain value, at a value using at how to say that, we can compute or evaluate the value of a function, a polynomial function, at given x using syntactic division. Okay, do I miss anything? 1x cubed, negative 9x squared, positive 24x minus 2. Okay, at 2, that will be 1, 2, negative 7, negative 14. You see, I do this without calculator. So this is 18. Okay, this is 18. At 4, 1, 4, negative 5, negative 20. This is 4, 16, 14. So at 4, that's 14. I don't make any miscomputation, right? You know what? Maybe I did it too fast. Just to make sure. Two. -7, -14, 20. Oh no, this is 10, not 20. So 20, 18. Oh yeah, that's correct. At 0, that's -2, so that's easy. Polynomial, the value of a polynomial at 0, that's basically the y-intercept is the same to the constant. Okay. Again. Okay. Uh, yeah. So from there we can already find where is it local max, local minimum. Okay. Local max. Actually, we can only say something about absolute max, absolute minimum. Absolute max is 18 at x equals to 2 and x equals to 5. Now, absolute minimum at -2 at I'm sorry, yeah, at x equals to 0, which is the endpoints, right? But to know the local max, local min, what you can do is you create the sign graph on the first derivative, okay? So between 0 and 5, we have two critical values, that's 2 and 4, okay? And then the slope at 0 is positive. The slope greater than 4, that's also positive. So this is negative. So local max at x equals to 2, so is 18. Local max is 18 at x equals to 2, and local mean is 14 at x equals to 4. Okay, now suppose you try to use the second derivative test. The second derivative, we see from that f prime x there, we get 3 times 2x minus 6. Okay, so f double prime 2 is negative, which means that's local max. That's local max at 2. And f double prime of 4, that's positive. You see, I don't even compute if it is what's the second derivative value at 4. I just want to see it's positive or negative. Okay, so local minimum at x equals to 4. Now the problem is this second derivative test is not applicable if our first derivative does not exist there. Okay, in other words, only if the critical number equals to 0. But if the critical number, how to say that? If the critical number comes from the first derivative equals to 0. If the critical number comes from the first derivative does not exist, then second derivative test is not applicable. Okay, that's for number 1. Let's go to number 2. I think that's the case we see in number 2. Fx equals to x square root of 1 minus x between -1 to 1. Okay, so the first derivative. You may want to identify that. So that's f prime x. So you're working on the realm of first derivative. Right, let me write it here. And then here, when you work on the realm of second derivative. Simply so that you don't confuse your informations from first derivative. Okay, so this will be by product rule, that's square root of 1 minus x plus x times 1/2 brought to the power of -1/2. Let me just write it underneath. And then the derivative of inside is -1. So this is equal to, if I factor 1 over 2 square root of 1 minus x. You try You try, okay? If you factor 2 over 1, if you factor 1 over, I mean, you know what? I write it down. So then this will be 2 times 1 minus x for the first term, right? And then for the second term, it will be just minus x, right? Notice that it becomes very, very clean. Okay, so there will be negative 3x plus 2 over 2 over 2 square root of 1 minus x, where the critical numbers then equals to 2/3 and 1, right? Yeah, but this 1 here is because the first derivative is undefined. This is because the first derivative does not exist. It gets a denominator equals 0, right? Okay, maybe I write it this way. That's the correct notation. Now, so when we do the second derivative, in case we do second derivative test later on, then we know it does not exist there. Using this first derivative, let me give myself some space. Using this first derivative, let's see the interval. Oh, actually, so f 2/3 equals to 2/3 square root of 1 minus 2/3. That's 2/3 times square root of 1/3. So 2 over 3 square root of 3. So that's 2 square root of 3 over 9. And then at 1, this 1 happens to be the endpoints also, right? So 1 square root of 1 minus 1. Oh, that's 0, duh. And then f negative 1 will be negative 1 square root of 1 plus 1. That's negative square root of 2. So from there we see that the absolute maximum is 2 square root of 3 over 9 at x equals to 2/3, and absolute minimum at the endpoints negative radical 2 at x equals to negative 1. Okay, let's do the sign graph to see the local max, local minimum. Okay, the sign graph on f prime x between negative 1 to 1. Okay, we have critical value at 2/3. So the first derivative is, sorry, I write it wrong. 2/3, the value there is 0. To the right of that is negative. To the left of that is positive. Okay, so we can see here that that's local max. Local max is 2 radical 3 over 9 at x equals to 2/3, right? Now, according to our textbook definition, then the endpoints negative 1 and 1 cannot be considered as local minimum. Okay, but in my point of view, we still can call that local minimum at negative 1 and 1. Okay, according to me. Why? Because if we just look at this domain here, if we only have that negative 1 to 1, we don't worry about anything to the right of that or to the left of that. You know, if we don't worry about anything to the right of 1 or to the left of negative 1, then yeah, of course, then negative 1 is a local minimum. Likewise, 1 is a local minimum. Okay, so let me write it down in different color. In my opinion, we can say, okay, local minimum at x equals to -1 and x equals to 1. Did I say that in the previous question about the endpoints? I didn't say that, huh? Yeah, I only say the one in between. But yeah, let me also mention that there. So in my opinion, what happened about the endpoints, right? In my opinion, we have local minimum also at x equals to 0, right? Because to the right is going up, means 0 is the minimum, right? And local maximum at x equals to 5. Let me box that so that you are aware that this may not be the answer that these authors actually agree with. Okay, that's for number 2. Let me draw the line to separate this. Number 3, I will do it slightly to the right here. Number 3, fx equals to 3x minus 4 over x squared plus 1 on -2 to 2. So the f prime x. Notice that in number 2 I didn't do second derivative test anymore. Okay, if you want to try, go ahead. But to get the local maximum, local minimum, then the relevance is that you can use the second derivative test to do local maximum, local minimum, right? Okay, but I did that already on the sine graph against first derivative, and we have only one critical numbers that we can use in the second derivative test. That's why it's just like, you know what, you do it yourself if you want to. Okay, now f prime x here will be the first derivative on the top is 3 times the denominator minus the numerator multiplied by the derivative of the denominator over the denominator square. The nice thing is the denominator is always positive, huh? Note, let me write it down. In other words, we will not get any critical number due to the first derivative becomes undefined. Okay, so this is 3x squared plus 3 minus 6x squared plus, actually, yeah, minus plus 8x over x squared plus 1 squared. That's negative of 3x squared minus 8x minus 3 over x squared plus 1 squared. Now, at this point, I really need you to be able to do factoring. Okay? So this is 3x and then x minus 3, I believe, plus 1 over x squared plus 1 squared. Oh, I forgot to turn on my light, my camera. You don't need to see me, but so that you know that you're not dealing with AI. Okay, then we get the critical numbers just from the numerators. So we have x equals to -1/3 and x equals to 3. Oh, the nice thing is this 3 is not in the domain, huh? So this is now because 3 is not in the interval of our conversation here. So we have only one critical numbers. Then f -1/3 is equal to -1 minus 4 over 1 over 9 plus 1. If I multiply by 9, you know what? -3 times 9, -27 over 1 plus 9. So that's negative 2.7. Okay, and then let's check the endpoints. Let me give myself space first. F negative 2 will be negative 10 over 5, that's negative 2. And F2 will be also over 5, 2, 6, 2. So that's 0.4. From there, we can already tell that the absolute maximum is 0.4 at x equals to 2. That's the endpoint. Absolute minimum is negative 2.7 at x equals to negative 1/3. Okay. Of course, from here we can also see right away that this absolute maximum, absolute minimum supposed to be local maximum, local minimum also. The thing is, what happened at negative 2, right? Okay. Of course, by just a simple observation, you see that at negative 2, negative 1/3, and 2, this is absolute max here. This is absolute minimum. Then we expect, of course, this must be local minimum also, right? And this must be local maximum. Okay, but what about here? Well, because there's no critical number there, then it has to be the local minimum. I'm sorry, local maximum. But let's check. Let's check. Okay, let's check. Let's check with the sign graph, right? Let's check with the sign graph. So the sign graph against sign graphs on f prime x, we see that it's 0 here, right? And then it's, what's that? It's positive there. So this is negative. This is positive. Is it right? No, the other way around. It's a positive here, is negative here. Right? So you see that the slope is, the graph is decreasing and then later on increasing. Therefore, it must be local maximum here, local minimum here, and local maximum at the endpoints. Okay? Again, I have to say it again, in my opinion, we can include the endpoints as our local maximum or local minimum. Okay? So let me insert more space. So in my opinion, we can say x local max at x equals to negative 2. Okay, now the textbook, I believe the textbook agree with me that the local minimum at x equals to negative 1/3. But for the endpoints, that's definitely local maximum. That's definitely absolute maximum. But can we call that local maximum? According to our textbook, they say no. Local maximum, local minimum cannot happen at the endpoints. But I mean, hey, it's absolute maximum. Why it cannot be the absolute local maximum? Yeah. Okay, let's go on. Number 4. Square root of x squared plus x plus 1 between negative 2 to 1. Okay, so number 4, fx equals to square root of x squared plus x plus 1 on negative 2 to 1. Okay, so we can rewrite this as x squared plus x plus 1 to the 1/2, right? Such that when we work with the first derivative, we get 2x plus 1 over 2 square root of x squared plus x plus 1. The thing is, I believe the denominator, this expression here is a positive definite, which means whatever x value you have, this must be always greater than 1. But how do we show that though? Because of course the coefficient, the leading coefficient is positive, right? Okay, a2 equals to 1 positive, which means the parabola opens up. But then at the same time, the discriminant is negative, means it doesn't have any real roots. So the discriminant is b squared minus 4ac. Okay, so it means it has no real roots, no real root. Okay, so it basically will never be 0. Okay, now then from there we see that, well, the critical number, therefore only x equals to -1/2, right? We only need to check the value at that critical value, critical numbers, square root of 1/4 minus 1/2 plus 1, that's square root of 3/4, that's radical 3/2. And then we check at the endpoints at -2, there'll be 4 minus 2 plus 1, that's radical 3. Oh, that's greater than. Okay, and at 1 that will be square root of 3 also, huh? Oh, okay. So absolute maximum at the endpoints, square root of 3 at x equals to -2 and x equals to 1. Please don't have this habit. So I know some students like to write it this way, at x equals to -2, 1, like that. When I saw that, I'm not happy. I don't like that though. Some instructors are okay with that, but please be more specific. Okay, don't write it this way. Just write it in a longer way. Okay, yeah, just write it in a longer way. X equals to -2 and x equals to 1, and then absolute minimum. I like to write in shorthand, but for that one, I don't know why. I just feel strange when we write x equals to like a couple numbers like that. Okay, so we are actually done with the absolute maximum log absolute minimum, and some consideration, some thinking. Then we know that, well, this must be local minimum. It's in the middle, so even our textbook will agree that we have to call that local minimum because it's not at the endpoints. Now, but what happened with the one at the endpoints? Our textbook will not call them local max, local min. Okay, but in my opinion, so let me box that again just to make sure that if you have different teacher that agrees with the book's opinion that the endpoints, local max, local minimum cannot happen at the endpoints, then you need to exclude the one I mentioned in purple. Okay, in my opinion, these are local max also. Okay, now that's for up to number 4. This should be enough, right? It should be enough with our practice here so far with number 1 to number 4. But let me do more. Okay, let me do more. So number 5, fx equals to x plus 2 cosine x in -pi to pi. So the first derivative will give us 1 minus 2 sine x. When I set it to 0, then sine x equals to 1/2, right? So x equals to pi over 6 in the first quadrant, or equals to 5 pi over 6 in the second quadrant, which is still in the domain. Okay, still in the domain. Oh, no, it's not, huh? Yeah, it is. -pi to pi. Yeah. Yeah. Okay, so those are the critical numbers. Let's compute the fx. So that's pi over 6 plus 2 cosine pi over 6. I think I need to settle with pi of some ugly numbers. Plus 2 square root of 3 over 2. So pi over 6, that's approximately 1/2, plus radical 3. That's pi over 6, sorry. This is pi over 6. At 5 pi over 6 is 2 cosine 5 pi over 6. Cosine is negative in second quadrant. Okay, so this is 5 pi over 6 minus radical 3. Okay, to get the more precise number, I need to use calculator. Okay, but I can estimate this. As I know, pi is approximately 3 divided by 6. That's approximately 1/2. Now, radical 3, hold on. 1.7 squared is 2.89. Now, 1.8 squared is 3.24. Okay, so this is between 1.7 to 1.8. Okay, let me make sure. Yeah, okay, and 18 squared. So this number is between 1.7 to 1.8. Put these things together, then this must be between 2.2 to 2.3 or 2, even 2.4. Okay, now how about this guy here? See, again, I don't use calculator. Okay, but since you have calculator, just use your calculator. Do it to 5 decimal places. But later on, when I say what is the absolute maximum, absolute minimum, I need to give the exact value first anyway, right? Before I give the decimal if necessary. So approximately 1/2, actually 3.14 times 5 is 15.7 divided by 6. That will be what? 2.2 for 12.61, approximately 2.61 minus a number between 1.7 to 1.8. Okay, so this will be approximately 0.9, okay, or 0.8, around that number. Okay, and then how about f pi? That will be pi plus 2 cosine pi, but cosine pi is -1. So that's pi minus 2. Pi minus 2, 3.1 something. That's approximately 1.14. Oh. And then f negative pi. Oh, sorry, that's positive 2. Duh. So that will be 3. Yeah, cosine pi is negative. It's negative, right? Yeah, so that's right. And then at negative pi, that will be negative pi plus 2 cosine negative pi, which is the same to cosine pi. So this will be negative pi minus 2. This is the one approximately -5. Okay, so using this approximation, I get some feeling like what they are. Absolute maximum is which one? Yeah, absolute maximum is this guy, huh? Yeah. Pi over 6 plus radical 3 at x equals to pi over 6. Absolute minimum is negative pi minus 2 at x equals to negative pi. Okay, you know what? Let me clean up a little bit my notation. So this is for this guy. I don't need this for now. This is for this guy. Okay, so between, and this is between instead of subtraction, right? Okay, then with that said, yeah, we get the absolute maximum, absolute minimum. But how about the locality, right? So we do the sign graph on f prime x from just negative pi to pi, and we have two critical numbers in between. Okay, that gives us 0 there, right? And then we see f, this is positive here, and then this guy here is negative. Oh, something not right here. Am I miscomputing something? Am I miscompute something? Hold on. Yeah. Oh no, I should not look at that, huh? I happen to look at the the positive negative. I happen to look at that. So no, that's not appropriate. When I put pi here, that's 0. So that's positive 1. So yeah, this is positive here. When I put negative pi, that's also 0. That's positive here. So it's negative here. Okay, so then from there we see that it's local max at pi over 6. Of course, it's already absolute maximum there, right? And then a local minimum at x equals to 5 pi over 6. Okay, but then in my opinion case, we have local minimum at x equals to negative pi. It's absolute minimum there, so it should be, right? And local maximum at x equals to pi. At the endpoints, are they local max, local min? Okay. Let's see number 6. Yeah, when it comes to trigonometry, yeah, you just learn it in pre-calculus, right? So be a bit careful. So we have fx equals to sine x plus cosine squared x in the interval from 0 to pi. Okay, so f prime x will be cosine x plus 2 cosine x times negative sine x. Okay, that gives me a chance to factor cosine x out, right? So the critical numbers happens first at cosine x equals to 0 or at sine x equals to 1/2. Okay, cosine x equals to 0 happens when x equals to 0. No, at pi over 2, my bad. Okay, in that interval, and then sine x equals to 1/2 happens at pi over 6 and 5 pi over 6. My apologies. Notice that to find absolute maximum, absolute minimum, you don't even need to look at the sign graph on the first derivative. You just compare the value in all of them. But if you want to use second derivative view, like let's do it. So you see that we have critical numbers here, right? Okay, all of them because the first derivative equals to 0, then the second derivative is actually quite convenient to use. Okay, second derivative will be, well, may not be that easy, huh? So negative sine x, I need to use product rule, plus derivative cosine x times derivative of that 1 minus 2 sine x, that is negative 2 cosine x. Okay, so this is negative sine x plus 2 sine x, 2 sine square x minus 2 cosine squared x. Which, if you happen to know, that is, I would be so happy if you know this, because you should know this. This is negative 2 cosine 2x, double angle formula. Okay, cosine 2x has three variations. The first one is cosine squared x minus sine squared x. The second variation is 2 cosine squared x minus 1. And the third variation is 1 minus 2 sine squared x. Okay, I do expect you to memorize that though. Okay, go back to your pre-calculus, your trigonometry. Okay, we actually don't need to simplify that. You can just plug in numbers, but it will be nice if you can simplify then plug in numbers easier. Okay, so the second derivative at pi over 2 will be negative sine pi over 2, which is negative 1, minus 2 cosine pi, which is another negative 1. So this is positive 1. From there, we see that it will be the second derivative is positive, so that will be local minimum, huh? At x equals to pi over 2. But when I plug in pi over 2 here, this is that's 1. Now then the second derivative at pi over 6, that will be negative sine pi over 6 minus 2 cosine pi over 3. That's negative 1/2 minus 2 times 1/2. That's negative 3/2. Right? So then from there we say that's local maximum at x equals to pi over 6. Now when I plug that number in here, that will be 1/2 here. I'm sorry. Let me use different color. So sine pi over 6 is what? That's 1/2. Cosine pi over 6 is radical 3 over 2, which when I square it, I get 3/4. So that will be 5/4, huh? The value is 5/4. Oh, that's even, yeah, that's higher, huh? Okay, and then what about the second derivative at 5 pi over 6? Second derivative at 5 pi over 6 is negative 1/2 for the first term, minus 2 times cosine 5 pi over 3. Oh, that's quadrant 3, quadrant 4. Okay, so this is negative 1/2 minus 2 times 1/2. So negative 3/2. Huh? So that's another absolute maximum, local maximum, which I start questioning my answer though. 5 pi over 3. Yeah, that's quadrant 4. So that's positive. Yeah, so that's local maximum also. But at 5 pi over 6, this is 1/2. Cosine 5 pi over 6, that's quadrant 2. Negative, but I square it, so square root of 3 over 4 anyway. That's 5/4 again. Oh, okay. I don't expect that though. Something may be wrong here. Something may be wrong here. Oh, no, 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 no. Duh. The reasons I say that it may be something may be wrong is because I somehow had in mind that 5 pi, between pi over 6 and 5 pi over 6, there's no other critical numbers. It's kind of strange to have local maximum next to each other. Okay. Uh, because think about this. If this is local max, I'm saying that my mistake is I thought that the critical number pi over 6 and 5 pi over 6 are next to each other. While actually there's a pi in between. Okay, but uh, my logic earlier is this: suppose I have no more critical numbers next to each in between this pi over 6 and 5 pi over 6, and both of them local maximum. You see, because these are consecutive critical numbers, right? Okay, so if this is the slope in between is negative, it's kind of strange. This is local maximum, it's going down, the slope is going down, but you have another local maximum there. Doesn't make sense. Okay, likewise, if the slope is positive, right? So you have local maximum here, but then the slope after that is positive, then this won't be local maximum. Okay, until then I say, oh yeah, pi as another critical number is in between. Okay, and we know that's a local mean. Okay, so the slope are zeros here, and this is positive, negative. It's like this, right? Okay, and what happened at the endpoints between 0 and pi, as I remember? Is it right? Yeah, from 0 to pi, right? So from here we see about the absolute maximum. Okay, absolute maximum at actually, from there we see that local. Just look at the local maximum. Then absolute maximum, both of them 5/4. So 5/4 at x equals to pi over 6 and x equals to 5 pi over 6, while absolute minimum, we have local minimum here, but we need to check at 0 and at pi. At 0, you know what, before I do that, let me grab this first. Go down and observe first the value at 0. F0 equals to 1, and f pi equals to, I think it's also 1, huh? Oh, so it's absolute minimum at 1? Why I feel like something not right there? But maybe, huh? Hmm. Hmm. I just somehow think that it may be less than that though. Did I do any miscomputation? I honestly suddenly have no confidence on this. At x equals to 0 and 0, there's more. At 0, at pi over 2, and at pi. As if it says that this function here is oscillating between 1 and 5 pi over 4, which doesn't really make sense for me. You know what? Let me check with the graphing. I'm afraid I make mistake, some computational mistake. So yeah, that's why. So sine x, yeah, let me share with you my view here. Sine x. You can use GeoGebra for your graphing calculator. On that's geogebra.org, I think. Cosine x being squared. Oh, maybe because it's only between 0 to pi. Yeah. Yeah, only from 0 to pi. So it's from here to approximately here, right? Yeah, so let me just in that interval, just in from x equals to 0 to approximately 3.14. 3.14. So here, yeah, okay. And then that's true. In that interval, it's moving between 1 to uh, 5 over 4. Okay, so yeah. So that's for number 1 to number 6. Definitely the type of question you will see in your tests. Okay, it's a standard question. Those are standard questions. Now, let me go on to number 7 to 12. Okay, my class at this point only went up to 3.3 only, and because it's my weekend, let me start working on these lecture videos. Next week, if you want to have, hey, you know what, Thomas, I would like to see more examples about section from section 3.4, then you can come here. Okay, you can come here and try to see how I approach this. Now, number 7, limit x goes to infinity of 3x to the 4th plus x minus 5 over 6x to the 4th minus 2x squared plus 1. Now, I want to use a little bit of your knowledge from pre-calculus when you did rational functions, right? Okay, and we want to find what is the far ends behavior. At that time, I think they call that horizontal asymptotes, right? And it was said that if the degree of the numerator and denominator are the same, then the horizontal asymptotes, which is expressed by limit x approaching infinity or negative infinity for rational function, then the horizontal asymptotes will be y equals to the ratio of the leading coefficients, right? So we expect the answer here to be 1/2 later on. But the way I answer that using pre-calculus, that's because at that time we were told that's what will happen. But when we were told that's what will happen, okay, we were told the reasoning behind it is not, it's very intuitive. It's very intuitive. So will I accept this way of answering? Oh, Thomas, I use what I know from pre-calculus. Well, I may give you 1 point, but this is not the work you're supposed to show your instructor, okay? Because your instructor expects you to use a more scientific method instead of like using this is what I learned from pre-calculus method. It's just like how to say that, it's not scientific. It's not scientific. I learned it from there. It's but why what I learned there is true, you didn't explain it, right? So don't use that method, whoever your instructor is. Now, the way we approach this is by dividing the numerator denominator by the exponent on the denominator, by the degree of the denominator. So what I'm saying is we will divide under the condition of limit, okay? Each term on the top and at the bottom by x to the 4th. But Thomas, you know what I meant, right? Can I just skip that step? No. No. No, 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 no. Uh, do not assume your teacher will be so nice to think he or she knows what you try to say without you writing it properly. Okay, no, no, that's a wrong approach though. That's a wrong approach because that's bias, right? You know, the definition of bias is like you don't need to say it, but I already know it. Okay, imagine if your teacher says like, I look at your face and you actually curse me in your mind, so I fail you. No, that's not right. So do not use the argument that I don't need to write it properly, but you know what I mean. Okay, don't do that. Don't do that. That's that's dangerous. We are going to a very dangerous slope there. So don't use that argument, because that argument can cut you in another way, in a bad way. Okay, but so show the work, and you will be so proud that you can express what you have in your mind in writing also. Okay, that's a skill though. That's a skill. Plus 1 over x cubed minus 5 over x to the fourth. Maybe I write too small there, huh? Maybe I write it larger. Okay, so that will be 3 plus 1 over x cubed minus 5 over x to the fourth over 6 minus 2 over x squared plus 1 over x to the fourth. Now, you may wonder, Thomas, why do we need to write it this way? Because once you have x to positive exponent, okay, positive exponent, and you bring the x goes to infinity, it will go to infinity. Okay. Even though if you have x to the positive but odd, it will go to negative infinity as x goes to negative infinity. Yeah, imagine x to the cube, right? If x cube, negative infinity cube, you know that will be negative, right? Okay, now, but we don't want to deal with infinity. What we want to deal with is 0. Remember that x to the very big number, regardless positive or negative, 1 over x to positive exponent, okay, will go to 0 as x goes to positive or negative infinity. Think about this. Well, 1 over negative 10,000 or 10 million. That will be very, very close to 0, regardless if it is positive or negative. That's what we use. Okay, that's what we use. Now then, when we plug in the infinity, we approach x to infinity, we end up with 3 plus 0 minus 0 over 6 minus 0 plus 0. Notice I don't write the limit anymore because I plug in infinity as if, and we get the 1/2 as we expected earlier. Okay, to be more precise, what you learn in pre-calculus, actually borrowing the result from calculus, which you were not well explained yet there. Okay, when your instructor in pre-calculus say that, oh yeah, the far end behavior of rational functions, if the degrees on the numerator equals to the degree of the denominator, then the far end behavior will be equal to the horizontal asymptote, will be equal to the ratio of the leading coefficients, right? Okay, but that's actually the result being borrowed from calculus. Now your job is to show that result using calculus. Okay, so when they already borrow it there, you should not use what you borrow to borrow back. Okay, now number 8 is actually even more interesting. Let me try to write it larger this time. Limit x approaching infinity of t cubed minus t plus 2 over 2t minus 1 times t squared plus t plus 1. Notice that the numerator and denominator both have has degree 3, right? Okay, now the thing is, should we should we FOIL the denominator? In my opinion, you can. It's not wrong with that. Okay, but instead of thinking that way, let me do it this way. So I copy the numerator and divide it by t cubed, while on the denominator, I also have to divide by t cubed, right? Okay, but I write it this way. Divide by t and t cubed, t squared. I hope you see what I mean. Okay, such that then in the next step, this way I don't need to FOIL that first. Yeah, this way I don't need to FOIL that first. We basically do it by visualization. 1 minus 1 over t squared plus 2 over t cubed over 2 minus 1 over t times 1 plus 1 over t plus 1 over t squared, right? Then from here we plug in numbers, right? We plug in the infinity, that 1 minus 0 plus 0 over 2 minus 0 times 1 plus 0 plus 0. Is it right? Okay, that will be 1/2 again. Oh yeah, that's right, because the leading coefficient on the top is 1, the leading coefficient at the bottom is 1, is 2. So yeah, we did expect that. Nothing really new. Okay. Now, number 7 and 8 are both rational functions. Let's see next. Number 9. That's still rational, but there's some issue there. Number 9, let me write it even larger now. Why? Because we have our x approaching negative infinity. Let me highlight that so that you don't miss that. Okay, why I need to emphasize that? Inside the square root, okay, if x is positive, then the square root of x squared equals to x, right? But if x is negative, however, square root of x squared is equals to negative x. Try it. Imagine if your x is negative 2. Square root of negative 2 squared, that's equals to square root of 4, which is 2, not negative 2. So if this were your x, this is your negative x, right? Okay. Actually, instead of explaining it that way, I need to say it another way. We actually define square root of x squared, to be more precise, equals to absolute of x. Okay, which then is positive when x is positive, right? Is x equal when x is positive, if is negative x if x is negative, such that it becomes positive again. Okay, but let me just keep this one here. Let me make it a bit smaller. Okay, now then on the top I have square root of 4x squared plus 1, 3x minus 1. I will divide the top and the bottom by x, because the degree on the top is actually x, the degree at the bottom is still x, right? So this is equals to limit x going to negative infinity, square root of 4x squared plus 1 over x, and at the bottom I have 3x minus 1 over x. Okay, limit x going to negative infinity, the denominator, then I get 3 minus 1 over x, right? The numerator is the one you need to be careful. Okay, at the numerator, we need to rewrite that x in the square root form, but it's not square root of x squared, but negative square root of x squared. Okay, in other words, then we will get limit x goes to negative infinity of negative square root of 4x squared plus 1 over x squared. This is because the x is negative, going to negative infinity. Okay, if x going to positive infinity, then you just replace the x by square root of x squared without the negative. Now here I cannot plug in infinity right away because it will give me, according to order operations, it will give me infinity over infinity, which is undecidable. Okay, what I will do is, well, it's still under condition of limit, right? Okay, so I will do is 1 plus 1 over x squared over, that's under square root, by the way, 3 minus 1 over x. Then from here you plug in numbers. This is negative square root of 4 plus 0 over 3 minus 0. That's negative 2/3. That's the proper way to do the work. Okay, that's for number 9. Number 10, limit x goes to negative infinity of x squared plus x cubed. Do not just plug in infinity right away here. Let's see. If you do that, you are assuming that this is equals to limit x goes to negative infinity of x squared plus limit x going to negative infinity of x cubed. That's the way you think, right? But this will give you infinity. This will give you negative infinity. Now, infinity minus infinity, is it positive infinity or negative infinity or exactly zero or another constant? Okay, we don't know. It's this form is not determined. Okay, you may say, oh, but Thomas, limit x going to negative infinity of x cubed is larger, so this infinity here is supposed to be larger, right? And therefore, not so big infinity minus a bigger infinity is equals to negative infinity, but that infinity is not that big anymore. Is it the way you're all of a sudden our infinity depends on the size of how you write it? No, that's not how we're supposed to do it. No, no, that's not how we do it. Okay, the proper way to do it is you well, we have common factor. Let's do that first. So this question is not too hard, but it's easy for us to make mistake. Okay. Now then from here you see, oh, you know what? When it is when it is infinity negative infinity thingy, right? A limit of product, we can split that into product of limits. Okay, because yes, we will know the infinity thingy. The answer here will have something to do with infinity. We just don't know if it is positive or negative. The thing is, product actually deals with that very well. Subtraction addition does not. Okay, you may say yes, if it is to the fourth, yes, it will be positive infinity plus positive infinity, no problem, then it will be positive infinity, right? Okay, if that were 4, but if that's 3 here, we have issue with the positive negative. Now, but at this point, we can split them. X cubed times limit x going to negative infinity of 1 plus x. Now, this will be positive infinity, right? Times this will be negative infinity. The product of positive times negative infinity is negative infinity. Okay, but when you subtract them, no. Infinity minus infinity, we don't know. It's not determined. Okay, number 11. We have radical on the top. Limit x goes to infinity of square root of 4x squared plus 3x minus 2x. Okay, when this goes to, this will be, if we just plug in infinity, you will see this is infinity minus infinity, still not doable, right? Okay, still not doable. So it can be 0, can be positive infinity, can be negative infinity, it can be anything in between. So the proper way to do that is to multiply by the conjugate on the top and the bottom. The purpose is actually just to get rid of the radical first. Okay, and we hope something helps us later on to becomes a nicer value. Let's see. So this will be limit x goes to infinity of, you see on the numerator we will have 4x squared plus 3x minus the square of 2x is 4x squared. While on the denominator, there's no subtraction, it's addition. So on the denominator, we will have it becomes positive infinity nicely, right? But the thing is, when we combine the top, we end up with still 3x, which will give us infinity if we just plug that in. But at least at this point, it's a lot nicer already, because then we notice, oh, you know what? The degree on the top, the degree at the bottom are both x, right? The same case with what we have in number 9. Then from here, I will divide. Let me just go to the right just to save some space. Limit x goes to infinity of the top divided by x, the bottom divided by x. this becomes limit x goes to infinity of 3 big over. The bottom left, I will rewrite that as square root of 4x squared plus 3x over x squared. Notice that x goes to infinity means x is positive, right? Because x is positive, then then x can be replaced by square root of x squared. Okay? Plus 2 here. Now this is limit x goes to infinity of 3 over square root of 4 plus 3 over x plus 2, which will give us 3 over square root of 4 plus 2, that's 3/4. Okay, that's for number 11. Let me see number 12. Limit x approach infinity of sine to the fourth. Ooh, that's tough. Sine to the fourth x square root of x. Number 12. Actually, this question is harder. Limit x goes to infinity of sine to the fourth x over square root of x. When I see this problem, I have squeeze theorem in mind. So let me do it with using the first method by squeeze. Okay, by squeeze theorem. By squeeze theorem. That is sine to the fourth x is between, it's the even degrees, right? So at least 0, at most 1. Okay, so multiplying by 1 over square root of x will give us still 0 on the left hand side. This is sine to the fourth x over square root of x, and this is 1 over square root of x. When I apply limit, then yeah, the left hand side is already constant, right? So I don't need to apply limit, that's already constant. This is limit x goes to infinity of 1 over square root of x, which we know this is 0. So by squeeze theorem, limit x goes to infinity of sine to the fourth of x over square root of x is 0. Okay. If you have a choice, do it this way. If you have a choice, do it this way. Now, my second method is not recommendable, but I will use this question here to show you some details. But for this question in particular, please don't use this method. Okay, what I'm gonna do is do the following. Notice that if x goes to infinity, then square root of x also goes to infinity, right? Then what happened with 1 over square root of x? That will go to 0, in particular 0 from the positive side. Okay, so suppose maybe not in this question here. Suppose you have a question like this: sine to the fourth of 1 over x, and then 1 over square root of x. Let's say you have that. Then you use this, substitute that, call this u. So later on it becomes u sine to the fourth of, in this case it will be u squared. But then your u, because x goes to infinity, then your u will go to 0, like that. Okay. And actually I just try to relate that to this kind of question: limit theta goes to 0 of sine theta over theta. Do you remember what is this? This is equal to 1. Okay, but no, I'm sorry. I thought that I can manipulate it that way, but no, it's not necessary. Actually, the squeeze theorem is the only way. Squeeze theorem is the only way. Let me erase this then. But just to remind you that you may see this kind of things that you need to do. Okay, when x goes to infinity, then 1 over x goes to 0 positive. Okay, that's for number 12. Number 13. Sketch the graph of a function that satisfies the given conditions. And that could be a lot of functions like this. Okay, but I mean, how to say that? What they give us here may give us a different functions. So you may have different works, that's different graph that satisfy all of this. But let me try to organize what we have first. So F0, to organize that is basically to rewrite it. Okay, and then the critical numbers are f prime negative 2, f prime 1, f prime 9 equals to 0. So we have critical numbers there. The far end behavior, horizontal asymptote. So limit x goes to infinity of fx is 0. So very far to the right, it goes to x-axis. But when x approaching 6 from both sides, right? This is a notation. Then we have vertical asymptote here, negative infinity. You know what? Let me try to sketch that first. So let's say this is my x-axis. Okay. At x equals to 0, at x equals to 0, I use this. At x equals to 0, the graph, the x-intercept is 0. That's also the y-intercept. Okay, and we have horizontal tangent line at negative 2, at 1, and at 9. We have vertical tangent line at 6. Okay, and then to the left of negative 2, the slope is negative. So let me do the sign graph on f prime. F prime x, the sign graph. To the left of negative 2 is negative. It's 0 here. And from 1 to 6, f prime 1, so 1 is also a critical value, right? That's also negative here. And from 9 to infinity, that's also negative. It's positive from negative 2 to 1 and 6 to 9. Okay, so we know the slope already. From the concavity, f double prime x to 0, it's concave up. And then, from 12, also concave up. From 0 to 6 is concave down. This is from 6 to 12, also concave down. Okay. So from what I see here, between 0 to 1, negative 2 to 1, it's increasing. Okay, so let's say it's like this. Okay, at 1, that's a critical value. So it's critical value. The slope is 0. And then from 1 to 6, the slope is negative. Oh, it goes to negative infinity, huh? Infinity. So, okay, let's drop it down here. And according to the graph, from 0 to 6 is concave down. So let me fix it. Like, so it is like this then. It's concave down. And from it's concave down here. Concave up. Hold on. It's concave down to 0, and then it's concave up like this. So it is like this. It's like this maybe. Oh no 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 no. We have critical number there, so it's like this. Maybe like this. They don't tell us the. They don't tell us the. Like this. No, it's concave up. It says, concave up. My bad. My bad. Concave up. So like this, concave up. Does it satisfy already? Let me check. So to the left of -2 is concave up, but the slope is negative. Right at 2 is still concave up, but the slope is 0. Between -2 to 0 is still concave up, the slope is positive. From 0 to 1, the slope is positive but concave down. From 1 to 6, concave down, slope is negative. From 6 to 9, the slope is negative. No, 6 to 9, the slope is positive, concave down. But we have asymptotes here. So let's say it looks like this. A concave down, the slope is positive, and the critical number here, and the slope is negative here. But at 12, it changed concavity to positive. So maybe like this at 12. Okay, so we have inflection point there, right? We have inflection points at 12. We have inflection point at 0. Now this one here maybe, hold on. The slope is negative there, so yeah, so it's just like this. But there's a change of concavity. Oops, sorry, the last one is not correct. Okay, that's for number 13. So you see, I think it will be helpful if you do this first and second derivative for the sine graph in this notion here. Like it doesn't have to be to scale, but the cutoff is the same, in the same position. I think that's helpful. Okay, you notice that's what I did, right? Okay, that's number 13. Let's go on with number 14. Save some space. Okay, so, oh, this is important. This is important. It's even. Even means symmetric with respect to y-axis. I hope you remember that. Which means we will only graph the right-hand side and then copy paste that to the left. Okay? F0 is 0. Let me just put it there. F0 is 0. Okay. The first derivative is 2x from 0 to 1, which means it's positive, right? So from 0 to 1, it's positive here. From 1 to 3 is -1. That's negative. In fact, because it's constant, there will be a line. -1. So that's a line with slope -1. Okay, and then f prime x, when it is greater than 3, that's a line with slope 1, positive 1. Okay. Once we know how to do antiderivative, this is easier to do. But let's do it with this way first. Okay. The slope at 1 will be 2 if you approach that from the left-hand side, and it is increasing, It is increasing. Now then, at that point, the slope will be -1. It's because we know it's a line. and then from here it will be positive 1, like that. Okay. Now, because this is an even function and continuous, then continuous means then we know right at 1 and 3, okay, we know right at 1 from the left hand side the slope is 2, right? Here, limit x approaching 1 from the left hand side of f prime x equals to 2. However, limit x approaching 1 from the right hand side of f prime x is negative 1. So we know there's a corner there, but it has to be continuous. Remember, it says it's continuous. Okay. Likewise, what I did there. Now, so we know what happened on the right hand side. Now, then what do you do with the left hand side, Thomas? What I do with the left hand side, I copy paste this. Okay. Copy and then paste it, and then I wonder if I can reflect this though. There's no way, huh? You know what? Let me try. No, I cannot. Yeah, I tried to reflect it, but I cannot. Well, then I just do it manually then. I'll just do it manually. So at negative 1 and at 3, negative 3, it will be like this, right? And then it goes down to, the slope is 1 there, and then the slope is negative 1 here. Okay, but it's symmetric with respect to y-axis. Okay. There's a good guide to see the graph. Number 15. The function is odd. Okay, then this is reflect symmetric with respect to origin. With respect to origin. In other words, we can rotate that 180 degrees through the origin. Okay, now then let's take a look on the first derivative. The first derivative sine graph, it's negative between 0 and 2. It's negative here. Okay, and then greater than 2 is positive. It has right horizontal asymptotes negative 2, so the value later on will be negative 2. Okay, but about the concavity, greater than 3, it's concave down, and between 0 and 3 is concave up. Okay. So let's see what we can expect from the graph here. Well, hold on, because it's symmetric with respect to origin. Then oh yeah, then wait. They don't tell us if it is defined at 0, huh? Okay, if it is continuous at 0, then it must pass origin. Okay, but they don't tell us that it is defined at 0. Okay, so this is 0 here, and at this is the 2, and this is, let's say this is 3. When x goes very far to infinity, the value is negative 2. Let me use different color then. Okay, the slope is negative but concave up between 0 to 3. Maybe something like this. And then So the slope is 0 at 2, concave up here, but then starting from 3 it gets concave down. I need to be very careful here. Oh, see, concave down, but it will go to -2, huh? So, you know what? Let me pick this guy here and drop it down. And pick this guy here, drop it down. Like this. Okay, and then this is the horizontal asymptote, y equals to -2. Okay, so between 0 to 2, the slope is negative, concave up. Between 2 to 3, the slope is positive, still concave up, right? But from 3 to infinity, the slope is positive, yet concave down. Okay, now, because this is an odd function, I will grab this guy here and then copy paste and rotate. Sorry, copy, paste, rotate. Yeah, it's like this then, huh? Okay, and then move it this way then. Yeah, I need to make sure that it is, I don't imply that it is defined at 0, so slightly a bit to the right, like that. You see? Oh, I need to move it up 1. Yeah, basically, if the value here is -c, then this has to be positive c. Okay, and it has a horizontal asymptote on the left hand side, y equals to 2 then. Okay, let me make it smaller so it doesn't take too much space. Yeah, okay. To complete the graph, this is -2 and this is -3. Okay, again, I don't see that it says it continues everywhere. I don't see that it says, and that's the reason the graph may be split. Okay, may be split. But what happened, Thomas, if the passage or the question says it is continuous everywhere? Then I need to connect these two here, and it may look like this. And this is the origin, and becomes like this. Okay, basically just move this up and make it like this, instead. Okay, that will work if we insist on continuity, but it doesn't say, so it doesn't have to. Next one, number 16. Hey, we have a figure that is the graph of the derivative of the function. So this is not the fx itself, this is f prime x. The question is, from that graph, on what interval the function is increasing, decreasing. You know what? Let's remind ourselves on the theory first. F prime x is positive, means the function is increasing. I'm sorry, I said it wrong. If this is positive or greater than 0, then this is increasing, and vice versa. If it is negative, it is decreasing. The concavity f double prime x is positive. That implies the first antiderivative is increasing and the function itself is concave up. Okay, if this were negative, then f prime x is decreasing, this is concave down. Okay, what we have is the graph of f prime x, so we will need this, we will need this. Now, let's look at the question in part A. On what interval the f is increasing? That's the interval where the function, the f prime x is positive. That is between 1 to 4 and then 4 to 7, huh? Increasing on 1 to 4 union 4 to 7. With my explanation in class, because this the first derivative equals to 0 right at only one point here, some instructors may say, because if you look at the graph, it may look like this. The slope is increasing and then at 2 decreasing, and then it becomes slope is 0 at 4, right? But then after that it's increasing again. So if you pick any 2 points including at 4 and something else, the slope is always positive. So some instructors or maybe in more advanced calculus, I can say we can say that it is actually increasing between 1 and 7. Okay, I use purple there because some instructors may not agree with that. Okay, if you write 1 to 4 union 4 to 7, I will accept that. Okay, with some further thought, you will see that even at 4, at that one point, the slope is 0. But if you pick any 2 points, which means one of them cannot be 4, the slope will then becomes positive. Okay, where it is decreasing on 0 to 1, and then from 7 to 8. Can we say 7 to infinity, Thomas? No, because the graph doesn't tell us. Okay. Second, for what values does f have local maximum, local minimum? Local maximum means, see, if it is maximum means the slope actually change from positive becomes negative and 0 somewhere between. From positive becomes negative, then this must be the local maximum then, right? Local max at x equals to 3, 4, 5, 6, yeah, at 7, right? Local minimum, if the slope change from negative becomes positive, negative becomes positive. So x equals to 1. Okay, sketch the graph of f double prime. So from here, we sketch the graph of second derivative. So basically think of the derivative. Okay, I will use, maybe I use green color. Let me choose a green color. Okay, from 0 to 2, the slope is positive, right? But it seems like, yeah, this 0 to 2, the slope is positive. That's approximately 1. Okay, and then the slope goes down to 0 at 2. Okay, the slope of f prime x is negative from 0 to 4. Okay, oh, go to 0, huh? The slope goes to 0. And then becomes positive again. The slope is positive again there. And becomes 0 at 6. Right? And becomes negative from there on. So maybe something looks like this. Okay, that's the f double prime x. Okay, sketch the possible graph of fx. So can you imagine the graph that gives you this slope function? Or at least from here we know the maximum minimum already, right? So let's try. So at local maximum at 7, This is 7, local minimum at 1. And then the slope between 0 to 1 is negative. Okay, and then from 1 to 4 is positive. It's reached 0 at 4 and then becomes positive again. At 7, the slope becomes 0, and then from there, the slope is negative. Now I need to pay attention about the concavity. It is concave up from 0 to 2. Okay, from 2 to 6, it's concave down. I mean, 2 to 4 is concave down. Is it right? Zero to 4 is concave down. At 4, it concave up again. At 6, we have inflection point, right? And then it goes down. Okay. This is 6 here. Do we have? Yeah. And is there anything happen at 3? No. At 1? Yeah. So that's approximately, that's what it looks like, I guess. Okay, that's for number 16. Now, then from here, I will go on with the material that has to do with, especially section 3.2. Okay, show that this equation has exactly one real solution. Okay, let's define the function first that we will deal with. Okay, so let fx equals to 3x plus 2 cosine x plus 5. Now, to show that it has exactly one real solution, we're supposed to show two things. We need to show two things. First one, we need to show fx has at least one root. Okay, at least one root. So choose an interval at which you think it will give you a root. Okay, maybe let's see what is f0. When x equals to 0, this is 1, so this becomes 7. f0 is 7, right? f0 is 7. The first derivative is I'm guessing. The first derivative is 3 minus 2 sine x. But this is at most 2, so the slope is at least 1, then throughout, at least 1 throughout the interval. It is increasing, but at 0 it's already 7, so if I need to find the root, it must be to the left of that, right? It must be to the left of that. So let's say I choose x equals to maybe -5. I just make up numbers. -5. Okay, that's 3 times -5 plus 2 times cosine -5 plus 5. This is for sure, this is -15 plus -15 plus 5, then it will be -10 plus something. -10 plus 2 cosine -5, right? But this is at most, -8, is it right? Okay, at most -8. Okay, so there is a root. I think I need to say so by intermediate value theorem. By intermediate value theorem, there is a root between a root c between -5 and 0, such that you see f0 is positive, f-5 is negative, right? So there must be a c between that in that interval such that fc equals to 0, right? In this one interval here, we have one solution. Could be other solutions in other interval, we don't know, right? But at least now we show that we have at least one root. Okay, now the second step is we need to show there's at most one root. Fx has at most one root. Okay, now suppose, to contradiction, suppose fx has two roots, had two roots. So this assumption here, this supposition here will lead us to contradiction. Okay, call that C1 and C2. That means FC1 equals to FC2 equals to 0, right? Okay, by mean value theorem, of course, somewhere in between we need to say that this function is continuous everywhere and also differentiable everywhere, right? Okay, yeah. Maybe I say that fx is continuous and differentiable on all real numbers, right? So by mean value theorem, there is C3, call that C3, between C1, C2. Let me picture that first. So this is C1 and C2, right? And it's continuous everywhere and it has x-intercepts there. It means there's a point in between C3 such the first derivative equals to 0, right? In fact, that's not, you can use mean value theorem, but I prefer to say Rolle's theorem, by Rolle's theorem. There's a C3 between C1 and C2 such that f C2 minus f, no, such that f prime, such that f prime C3 equals to 0. But f prime x throughout the all real numbers turns out to be 3 minus 2 sine x, 3 minus 2 sine x, okay, which is at least 1. In other words, f prime x cannot be 0 for every x. Now, that leads to the contradiction. This is the notation for contradiction, by the way. Leads to the contradiction that f prime C3 equals to 0. Now, why we have that contradiction? Because we assume there were two roots. Okay, so fx has at most one root. Okay, now then by 1 and 2, it has at least one root and at most one root, then we can conclude fx has exactly one root. Okay, that's the intention of this question. Okay, but an alternative approach for step 2 to show that it has at most one root is by arguing. So alternative for step 2 is you show that need to show fx has at most one root, is by showing that f prime x is 3 minus 2 sine x at least 1, which is positive, which means f prime x, which means the function, the fx is increasing on all real numbers, right? Now, and because it's continuous, since fx is also continuous, on R, the same interval where they're increasing, then the only way that can happen then is fx is 1 to 1. Okay, which implies if fx has any root, that is the root. If fx has a root, that root is unique. That's the only root it has. Okay, no other roots. But the one I write in green here is not the intention of that question. Okay, it's not the intention of the question. Maybe let me say it this way: in your test in my class, if you show me step 2 and alternative of step 2, I may give you extra point. But the one I really want to see is the one I write in black here. Okay, let me go on. Number 34. Number 34. Suppose fx is continuous on that interval. Fx is continuous on 0 to 4 and 2 less than equals to f prime x less than 5 on 0 to 4. Well, notice that this implicitly f prime x, fx is differentiable, right? On 0 to 4 is differentiable on interval 0 to 4. Therefore, the mean value theorem is applicable in interval 0 to 4. Okay, so mean value theorem is applicable on that interval 0 to 4. Okay, which implies f4 minus f0 minus 4 minus 0 is equals to f prime c for c in between 0 to 4, right? Okay, that's mean value theorem. But f prime c, because it is between 0 to 4, is between 2 to 5, right? Using this, let me show you where I get that from. Now I will substitute that f prime c with f4 minus f0 over 4 minus 0, which is 4 is less than 5 but greater than 2. Multiply by 4. But what is f0? f0 is 1. Multiply by 4, and then I add 1. So f4 will be between 9 to 21. That's what we expect. Okay, that's for number 34. Let me go on. By applying mean value theorem to this function on this interval, show that this. Oh, okay, so proof f prime x is 1/5 of x to the power of negative 4/5. Okay, seems like we are approaching this from 32, huh? Okay, so hold on. Hmm. Hmm. Uh, F32 is 32 to the power of 1/5, that's 2. Okay. Uh, but how do I want to show this? How do I want to do this? Yeah, this basically try to say that the value at, if we define it this way, then the value at 33 is between 2 and 2.0125. That's basically what we need to get. Okay. So let's see. So by mean value theorem, what mean value theorem say to us first? Yeah, it's clear that this function is continuous and differentiable on this interval, right? But mean value theorem says that there is a c between 32 and 33 such that f32 3 minus f32 over 33 minus 32 equals to f prime c. Okay. So, but at the same time, notice that f prime 32 equals to what? That's 1/5 times 1 over cube 5th root of 32 to the power of 4. Is it right? That's 1/5 times 1 over 2 to the 4th. That's 16 times 5, 80. 1 over 80. In decimal, this is 0.0125. Oh, that may be something have to do with that. That's the slope. Actually, if I do the second derivative, of x, I find this is negative 4 over 25, x to the negative 9/5. This is negative on that interval 32 to 33. Why do I want to say that? Because the second derivative is negative, it means f prime x is decreasing, right, on that interval. Is it right? That also means f prime 32 is the absolute maximum. Is the absolute maximum for the first derivative. which is, what is the absolute minimum, is on that interval. Okay, now that implies, let me bring that here, that implies that f33 minus f32 over 1, which is what we call f prime c for some c in that interval, must be less than equals to f prime 32. Is it right? Okay. Oh, another thing is like, because f prime 32 is positive, then fx is increasing there. Okay. It is actually increasing throughout the interval on 32 to 33. The slope is increasing. I mean, the slope is positive, so the function is decreasing, but the slope at the same time is decreasing. Okay. But this is equal to, oh, because the function is increasing, then f33 must be greater than f32. Agree? Okay. So we already solved the left hand side. Okay, so 2 is less than fifth root of 33. What I'm about to do right now is to show that we have the right hand equality. Because f prime 32 is the absolute maximum, then any other number in here must be less than f prime 32. The derivative of any other number in this interval must be less than f prime 32. Okay, from there then I develop, well, divide by 1, so f33 must be less than f prime 32 times plus f32. Okay, so fifth root of 33 is less than 0.0125 plus 2. So this is the first part, this is the second part. Now, so by 1 and 2, we have proven that the fifth root of 33, of course, is greater than 2, but at the same time cannot avoid 2.0125. Okay, that's for number 35. Number 36. For what values the constant AB of this function here get 1, 3 is a point of inflection. So basically it is saying that y equals to a times 1 cubed plus b times 1 squared. This is equals to a plus b, but this is equals to c. Okay, that's our first equation. Okay, now then y prime equals to 3ax squared plus 2bx. It's point of inflection, so the second derivative equals to 0, right? So y double prime equals to 6ax plus 2b equals to 0. Okay, at 1, at x equals to 1. So in other words, we get 6a plus 2b equals to 0. Now that's our second equation. Okay, so how do we solve a plus b equals to 3 and 6a plus 2b equals to 0? You know what? Let me divide the second equation by 2. if I subtract, I get negative 2a equals to 3, so a equals to negative 3 halves. Am I right? Okay, and because a equals to negative 3 half, I put that back into the first equation. Negative 3 half plus b equals to 3, b will be 9 half. So y equals to negative 3 half x cubed plus 9 half x squared has point of inflection. Now let me write it properly. Point of inflection at 1, 3. Okay, you know what? Let me check. So y prime equals to negative 9 over 2x squared plus 9x, and then y equals to negative 9x plus 9. Yeah, if I set this equals to 0, I get x equals to 1. Right? Okay, and then just need to check y at 1. There will be negative 3 half plus 9 half. That's 6 half. That's 3. Okay, good. I think I will not do the 3.5 then. Honestly, I'm a bit tired. It's more than 2 hours already. So let me just delete this for now. I will do that in the next, the review B. Okay, but number 37. Let gx equals to f x squared, gx equals to f of x squared. So this is a compositional function where f is twice differentiable. It means f prime x exists on all real numbers, and f double prime also exists on all x. Okay, and we are given that f prime x is positive for x not equals to 0, and the function is concave downward on the left hand side. Let me just write do it this way: downward there and upward here. The slope is always positive. The slope is always positive, concave down here and then concave up. So it seems to be like that, huh? Okay. For what numbers does g have extreme value? Extreme values. So the first derivative then, part A, g prime x equals to f prime x squared times 2x, right? Oh, actually, they say that f prime x is positive for all x not equals to 0. But at the same time, it is differentiable even at 0, which means f prime 0 has to be 0 then, right? Okay. Cannot be negative because the second derivative exists. The second derivative exists means f prime x is continuous on all real numbers, right? Is continuous on all real numbers too. Okay. So when will this function has extreme values? Concave down, concave up, 2x, f prime x squared 2x. Extreme values means the first derivative equals to 0, right? Right? Mm-hmm. Now, f prime x squared is positive, right? For x not equals to 0. Now, we don't know about f prime 0, but we know at 0, g prime 0 will be 0. Okay, so critical numbers at x equals to 0. And it is continuous at 0 though. Okay, at what numbers does g have extreme values? The way they say it is like they use the word numbers. So is there more than one though? I don't see reasons. Yeah, the thing is the first derivative is positive all the time. Oh, so when we have x squared, hold on. This is for f, right? This is for f. Now notice then g, because that's x squared, it becomes an even function, huh? Okay, so this later on becomes, so if the graph looks like this, I need to reflect this though. I need to reflect that. So it will be like this then, right? Okay, that's the minimum. That's absolute minimum. In fact, yeah, that's the absolute minimum. Okay, so g prime x equals to 0, g prime 0 equals to 0. Okay, but let's take a look what happened to g prime x in the surrounding area. Okay, so what is the g prime positive? If I pick a positive number, that's f prime positive times 2 times a positive number, that's positive, right? And on the left hand side, f prime uh, x squared. If x is negative, the x squared will be positive, right? Times 2 times negative number. So this will be negative. So the slope is negative on the left hand side. The slope will be positive on the right hand side. So this will be absolute minimum. Absolute minimum at x equals to 0. I don't see any reason we can get anything else there though. Yeah, I don't see any reason we get anything else. The first derivative is positive. Yeah, I'm really bothered by this. I'm really bothered by this. I'm really bothered by that. I need to think about this a bit further. Really. Yeah, I need to think about this a bit further. It seems like there is some details that I didn't catch. The thing is, yeah, what happened here is it basically makes the gx becomes an even function. You know, the gx becomes an even function. Let me show you. So gx is even. Why? Because g negative x equals to f negative x being squared, which is equals to f x squared, which is gx, right? Okay. So we just need to focus on the right hand side for now, and because the first derivative of the function is positive, so it is increasing, and concave upward, it's concave upward. When we reflect that to the left hand side, it will concave upward also, you see. Okay, because it's twice differentiable on all, it must be continuous on all. If it has any extreme value, there will be only at 0. That's the way I see. Okay, so I wonder why they use F here. Now discuss the concavity of G, as what I have said earlier there. Yeah, because since Fx is concave up on 0 to infinity, then Fx squared, of course, is concave up on 0 to infinity also, right? Because x squared will be positive, okay? On the other hand, G x is even. That implies gx is concave up also on negative infinity to 0. Okay. In other words, the gx is concave up on negative infinity to 0, union 0 to infinity, but one point does not tell us the concavity. So this will be concave up on all real numbers. At least, honestly, that's my opinion. Okay, but let me think about it a little bit. I have no other way out. So yeah, I really question why they put a plural numbers for G for having extreme values. Okay, or maybe that's because of the grammar only. Okay, but this is what I get. Okay, let me stop here. Then I will continue in future for the other questions in this chapter 3 review.